Welcome to this short supplement of video demonstration 4. In video 4 we showed you some complex set structures, but we didn't show all of them executing. In this video we've taken some of the more unusual set manipulations and put together some simple examples to illustrate how they work. Let's jump right in. We're going to look at some examples involving ordering of sets. I've set this up in advance. I've got two sample sets here, A and B. If we just take a quick look at both of them, if I put this one in here, you can see that it contains four numbers, 22, 33, 44 and 33. So the 44 is the largest, the 22 is the smallest, and the other two are equal. Let's do a few operations against that set. We're going to do some rankings. If we put a ranking in here. There are several different ways in which you can rank sets, and it all depends on how you deal with matching elements. I'm going to show you the different variations. In this first case, we're doing a standard ranking. If I click on this, you can see that the first place is 1, the last place is 4, and then the other two are equal second. If I get rid of this, and we do something like a modified rank, we run this. In this case, those two equal numbers are now equal third, not equal second. That's called a modified ranking. If I look at another one, if I look at a fractional ranking, then basically what it does is split the difference. You can see here, first place, fourth place, and the other two are 2.5. Get rid of this. Let's look at an ordinal ranking. What this one does is just pick one to be ahead of the other. So here you've got a 1, then a 2 and a 3, then a 4. Then the last option, or last alternative, is a dense ranking. And basically you squeeze them all up. If we click this, you can see we've got first place equal second, and then this next one is equal third. I have no opinion on which one's better. They all have their uses. But that's how we deal with rankings. And again, I'm showing some very simple examples just to make it clear what's happening here. But obviously we can do this with much more complex and larger sets if we had to. Let's take a look at this second sample set. I'm going to show you some other examples. This set just contains the numbers from 1 to 20 in order. First thing I'm going to do is, let's clear this out. We're going to look at some quantiles. If I were to look at quartiles for that set, basically what we're going to do is we're going to allocate each of those 20 numbers into the quartile. Now for convenience, you saw that I had it ordered in increasing order. So if we click on this, you can see that in terms of quartiles, we've got 1, 2, 3, 4, 5 elements are in the first quartile, 5 in the second, 5 in the third, and 5 in the fourth. If we clear that out, use quintiles. This all works the same way basically. We run it with quintiles. Now we've got 4 in the first, second, third, fourth, fifth quintiles. Let's clear that out. Same thing with deciles and percentiles. I'm going to show you deciles. 1, 1, 2, 2, 3, 3, 4, 4, all the way up to 10. So that's all fairly straightforward. I'm going to show you one other variation, and that is a Winsorized group, a Winsorized set. If I apply a Winsorized set in here, basically you tell it what the source set is here, and you apply a minimum. We're going to apply a minimum of 4, and let's make the maximum 13, let's say. Now what this does is it basically sets a floor to the values that are below 4, and it sets a cap to the values that are above 13. And if we run this, you can see that 1, 2, 3 have now become 4, and everything else keeps the same. And then 14 through 20 have now all been set at 13. Next, we'll take a look at set matching. This covers things like unions and intersections, but it's much more generalized. I've set this up ahead of time, this program back here. And I've also set up some sample sets that we can see for some examples. First, I'll just show you quickly what they contain. They're all fairly small. They contain a set of numbers. This first one, A, you can see that it has the number 1 duplicated and the number 7. If I clear this out, set B consists of these numbers here. And I'm going to show these to you while we go through the examples, that they'll be on the bottom of the screen. So set C, 1, 4, 24, 24. This one duplicates number 24. Clear that out, and let's look at the last one here. 1, 3, 7, 17, 24, 26. So what we're going to do is we'll do a variety of different matches against these sets. So you can see over here on the left, we've got 4 different variations. We've got something that allows you to take a set and make sure that it matches against only an element in one other set. You can match it against several sets, by the way. You can do it so that it matches no sets, or it matches all of the sets, or you can even set it up so for each element we check to see whether it matches in n sets. You can either choose n to be exact or n as a minimum. Let's start by looking at match no set. If I put this in here, it asks me for a number, and then we're going to specify which sets that we're looking at. So this first was we're going to put sample set A in here, and then we're going to put sample set D in here. And if we run this, we see that elements 2, 4, 10, and 13 are in A but not D. Let's look at something different. Let's look at match 1 set. This is a number 2. And what we're going to do is we're going to match the same 2 sets, this one here and this one here. When we run this, we see that elements 1, 1, 7, 7 are in the result because they both repeat in the first set and the second. They both repeat in the first set, but they also exist in the second set. Let's clear this one out. Let's do another match. Let's do another match of 1 set, just out of curiosity. But this time we're going to match this set against this set. And here we get 1, 1, and 4. And in this case, we have 2 elements, 2 occurrences of 1 in the first set, but there's only 1 occurrence of 4 in set A. And obviously 1 and 4 both occur in set C. You can do this to as many sets as you like, obviously. As you've seen previously, we have the ability here to add multiple sets to an invert, multiple twins, and the actuator knows how to deal with all of these. Let's clear this out. Let's do a match of none this time. We're going to match none. This is a number as before. And we're going to match set A here against set D here. So now we're looking for elements in A that don't occur in set D, 2, 4, 10, and 13. Close this out. Now we'll look at match n sets. This is the most generalized one of the lot. As you can imagine, the logic underpinning this is very, very complex. So we'll put sample set A in here. We're going to look at sample set B in here. And let's look at a third set here. We'll put it in there. And we're looking for elements that match just 1 set against set A, the target set. And we get just 2, 7, and 13. And again, 7 is repeated because it occurs twice in set A. And obviously we have the ability, you've seen before, we have these unique subsets. You can always strip out duplicates from a set by just applying it to a unique subset. Now, instead of 1, let's change that to 2. So now we're looking for elements that occur in both of these sets. And you can see that 1 occurs in all 3 of the sets. So it occurs in both the matching sets as well as the target set. And in the target set is duplicated, so you see a 1 and a 1. Incidentally, All of these items you see are shaded in blue in the library. This means that they can be used in a generalized synchronized sort to drive a subset of related sets in the same group. So you can see this is starting to get very, very powerful. You've now seen some varied examples of set manipulations, and as with all other inverts, you can use these constructs anywhere in an invert structure, and there's no logic needed from you. Thanks for watching, and we'll see you soon.